You're watching the second lesson in Mix and Flow of Matter. In this lesson, we'll be discussing mixtures, defining mixtures, and differentiating between different kinds of mixtures. So first, I'd like to start off with a picture like this. This is sort of a flowchart showing you how matter can be divided. So matter can be divided in two ways. You have your pure substances, and you have mixtures. Now, we'll go into more detail as we move along, but pure substances are things that are just made up of one thing. So we'll go to our previous example when we talked about states of matter, iron. Iron, right? With iron, with an iron bar, it's only iron in it. So you can call that iron bar a pure substance because there's only iron atoms in it. Or only one type of molecule. So you can call salt a pure substance, even though salt is made out of two different atoms, sodium and chlorine. You can call it a pure substance because you'll only find those combinations of atoms together. Then you have something called a mixture. And a mixture is when you have different atoms, compounds, molecules combined together in one spot. And they may not be bonded and they may not even be closely related, but they're together in a, mixture. Mixtures can be divided into homogeneous and heterogeneous mixtures. And we'll go into more detail as we move along. But you should know what a pure substance is. You should know what a mixture is. Homogeneous and heterogeneous mixture is. You should also probably copy this flowchart down. It's a good way to visualize what this lesson is talking about and reviewing. So, pure substance. A pure substance is anything that is made up of one kind of atom or molecule. So again, our salt example. All of this salt is just NaCl. Yeah, two different types of atoms, but they're connected in a molecule, NaCl molecules. And these molecules make up all of this salt. Makes up all of this salt. So it's a pure substance because it's only salt. Gold bars is another example. These gold bars, in these gold bars are just gold atoms, right? You're not going to find iron and other types. Well, you might, but like let's just say for the purpose of this example that it's pure gold, there's no other atoms in it. So you only have gold atoms here, so it is a pure substance. It is pure because there's only one substance in it, one kind of atom or one kind of molecule. Mixtures are when you have more than one pure substance put together. So you take two pure substances. For example, let's say you take salt, right? This pure substance of salt, and you add it to water. Well, you have salt molecules and you have water molecules, and you put them in the same spot. You've made salt water, right? You have two different molecules taking up the same spot. A glass of salt water has water molecules and salt molecules. And so both of those molecules put together, floating around with each other, results in a mixture. And mixtures, sorry, that was terrible. Mixtures can be homogeneous and can be heterogeneous. And again, we will define them as we move forward. But know that mixtures are when more than one pure substance are found together. Again, salt water is a good example of that. So, homogeneous. What does that word mean? Well, if you break up the word homogeneous, well, it means looks the same, right? Looks the same or alike. So a homogeneous mixture, again, you should know this, a homogeneous mixture is a mixture whose parts cannot be found. So my example here would be lemonade. When you look at this glass of lemonade, now ignore these slices of lemons and the ice, but look at the liquid in the middle here. How do you make lemonade? You take lemon juice, water, and sugar, and you mix them all together in a jug. Can you see the sugar, sorry? Can you see the lemon juice? can you see the water separately? Can you see those different layers? No, it looks like one thing. It looks like lemonade. So it's homogeneous. It looks alike. It looks the same. It looks like one thing. So homo means same, genius means makeup. So it's homogeneous. It's the same makeup. It looks like it's the same. So a homogeneous mixture means it's a mixture that looks like one thing. So another word for a homogeneous mixture is a solution, right? So again, you can call lemonade a homogeneous mixture, or you can call lemonade a solution. An example would be salt water. If you mix salt water very well, it just looks like water, right? You don't see the salt floating in unless you put too much salt in. Sugar water is another example. You don't see the sugar unless you put too much sugar in. So it looks just like water. So it's homogeneous. It looks like one thing. Or you can call it a solution. Heterogeneous mixtures. Well, what does that mean? Well, all that means is looks different. Heterogeneous mixtures are mixtures where the parts can be seen. And so here we have a picture of trail mix. And this would be a good example of a heterogeneous mixture. Because you can see in this grouping, in this area, in this mixture, you have peanuts, you have Smarties, you have raisins, you have different kinds of Smarties, you have almonds, you have cashews, and you have all these different things that make up the trail mix. You have different things that make up this mixture. And you can pick them out. You can point at it and be like, that's a different part, that's a different part, and that's a different part. So if you can do that in a mixture, it's heterogeneous. Hetero means different, genius means makeup. So it's different makeup. It has a different makeup. You can see the parts, right? And we go back to our first example, lemonade looks like one yellow liquid. Trail mix, you can see what it's made out of. And that's the difference. Homogeneous mixtures or solutions look like one solid or one thing, while heterogeneous mixtures look like multiple, you can see the different parts of it. This video will go over more detail on that. You can check it out on D2L and on my notes. Heterogeneous mixtures can be broken down even further. So you can take heterogeneous mixtures and you can either call them mechanical, suspensions, or colloids. I know this is a lot of information, so if you need to review, please just keep rewinding and checking out the different terms. But you do unfortunately need to know this. You need to know that matter can be broken up into pure substances. So if we go back to the top, matter can be broken up into pure substances and mixtures. Mixtures can be broken up into homogeneous mixtures or solutions, or heterogeneous or heterogeneous solutions. And those heterogeneous solutions can be broken up even further into mechanical, suspensions, and colloid mixtures. So we'll talk about those. Mechanical mixtures, again, just like before, the trail mix, this is when the parts are really easy to see. The parts aren't blended in. You can see in this trail mix, pretzels and Shreddies and candy and Reese's Pieces and popcorn. You can point out at each different part. If you can look at it and go, well, that's a different part, and that's a different part, and it's very easy to see, then you have a mechanical mixture. It's just trail mix. If it looks like a bunch of stuff scattered in one area, it's a mechanical mixture. Suspensions are a little bit more difficult. This is a type of heterogeneous mixture. It is a heterogeneous mixture when parts of the mixture will eventually settle at the bottom. So here we have mud and water. And this mud-water mixture looks homogeneous, right? It looks like one brown liquid. Well, over time, the mud and the dirt will settle at the bottom, right? That mud and dirt is hitting the bottom of the glass and is settling. And now you can see the different parts. You can see the water and you can see the mud. Before you couldn't, and eventually over time, it became easy to see the parts. So the mud is floating around in the water like so. And as time moves on, more and more mud is being piled up at the bottom until all you can see is the mud at the bottom and the water at the top. So a suspension at first looks like a solution or homogeneous, but over time, the particles, the mud, the other parts of the mixture will settle down at the bottom. So if I were to ask you on a test, for example, is mud and water or dirt water or sand and water a heterogeneous or homogeneous mixture? Well, then you would say it is a heterogeneous mixture, and it's also a suspension because the dirt, the sand, the mud, whatever you have, will eventually hit the bottom. The next type of mixture is called a colloid. Now, a colloid is are mixtures where the parts are floating, but they're so small. The parts that make up the colloid are so small, the parts don't settle. And so they look like solutions. They really do, because they don't settle. They look like one thing, but the parts floating scatter light, so they can be detected. So here we have an example of a colloidal mixture, flour and water. If you mix just enough flour and water, it won't settle. What happens is the light will scatter in a flour-water mixture, but will flow easily through, or move easily through, a solution of water and sugar. You don't need to know this specific word. You don't need to know that this is called the Tyndall effect. You just need to know if you were to tell the difference between a colloid and a solution, you would say, and I might ask this on a test, you would say, well, if I had to tell the difference between a solution and a colloid, I would shine a light through it. And if I shone a light through it and the light scattered, then I know I have a colloid. And so it's heterogeneous because I can detect the different parts. It's not just enough to see the different parts. If you can detect them, if you can say, oh, well, the light finds it for me, then it's heterogeneous. A solution, even if you use light, you still can't find the different parts. So a solution will still be hard to tell, and it will still look like one thing. So this is just going to be a quick review thing we'll do in class. And then from there, we'll jump onto dissolving. So this is the process of making mixtures. So dissolving, what that means is when you take a solid, and it's broken down when placed in a liquid. So for example, you take salt or you take sugar and you add that to water to make a solution. Well, the crystals of salt and the crystals of sugar break apart in the water and they start floating in the water. And so because of that, you can't see the sugar, you can't see the salt, and the crystals have dissolved or broken down. The molecules have broken apart and are floating in the liquid. So dissolving is when a solid is broken down when placed in a liquid. Sorry, I have a bit of a sniffle. So, this is a bit of vocabulary you need to know. When you are dissolving things, for example, sugar in water, you call the liquid that is dissolving, the thing that is dissolving the solid, the solvent. And when you refer to either the solid and you can dissolve gases, a solute. So let's go back to our first example, sugar water. As you add sugar to the water, the sugar dissolves. So what is the liquid dissolving? Water. So the water is dissolving the sugar. Okay, so if the liquid, water, is dissolving the solid, the sugar, the liquid water is the solvent. And the thing that's dissolving the sugar, which is dissolving into the water, is the solute. So you add solute to a solvent. You add sugar to water. You add salt to water. The salt dissolves, so that's your solute. The liquid doing the dissolving, in this case water, is your solvent. Now you may also notice that I say gas. Gases can also be dissolved. An example of this would be Coca-Cola, right? Coke bottles, when you open the Coke bottle, you hear that tss. That's the gas, the carbon dioxide gas, basically escaping from the bottle. And it has been dissolved into the liquid. So the Coke, the liquid Coke, would be your solvent, and the carbon dioxide gas would be your solute, because it is dissolved in the liquid. So, for something to dissolve, the molecules in the solid need to be attracted to the liquid. It is in the molecules in the liquid to pull away from the molecules in the solid. So when you add, again, we go back to sugar water, when you add sugar to water, at first, all those sugar molecules are attached to each other, they're connected to each other. And as you put it in water, well, the water breaks those bonds, and the sugar is now attracted, or the water is also attracted to the sugar. So the molecules of sugar are separated and they're floating away from each other. And there you have dissolving, because the water is attracted to the solid, the solvent is attracted to the solute, and breaks those bonds apart so that they are floating in the liquid. So when something can be dissolved, we call it being soluble. We say it is soluble. If it can't be dissolved, it is insoluble, right? So sugar and water, again, dissolving sugar into water. The sugar is soluble because it dissolves in water. Salt is soluble because it dissolves into water. What's something that doesn't dissolve into water? Now, for example, let's say sand. Sand doesn't dissolve in water. You see it on beaches, you see it in the ocean, it's floating around. Well, then you could say that sand is insoluble. It doesn't dissolve. It doesn't break apart. So this is a picture of, sorry, I almost fell off my chair. This is a picture of salt being dissolved. You can see that the sodium and chlorine atoms are being ripped off by the water molecules, and you can see that the water is surrounding our sodium and the water is surrounding our chlorine. And you don't need to know this word, but this salt crystal is being torn apart by the water and is now floating freely in it. So it is being dissolved. You'll no longer see this crystal because the atoms are now floating freely in the water. So a quick question I'd ask is, how could you affect how things dissolved? Right? If the water is moving to the salt crystal, and then the salt crystal is breaking apart and moving away from itself, how could you make that faster? Right? What would affect its movement? And this, as a hint, I would say, think about what changes the movement of molecules in a substance. What changes how they move? I'll give you just a couple seconds to think about that. Okay? So hopefully you thought of energy, right? As you add energy, if you add energy to this mixture, the water molecules are going to move faster, which means they're going to be attracted to the salt crystal faster, meaning that they're going to pull away the atoms from the salt faster. So as you increase temperature, you increase dissolving, right? So this would be one of the big things that affect solubility. Solubility is a word we use to say how something dissolves. So if you increase temperature, you increase solubility. You increase how fast something dissolves. The size of the molecules. Large molecules dissolve relatively slower than smaller molecules because they have less surface area and larger volume. And you'll talk about that in math. So you just need to know molecule size. Big molecules dissolve slower than small molecules. Movement, which is also related to temperature, because if you increase the movement of the molecules and the atoms, then it dissolves faster. And temperature increases the movement or affects the movement of the molecule. So if you decrease the temperature, you lower the solubility because the molecules are moving slower. Pressure is unique in that it only works for gases. Adding pressure or squeezing sugar or squeezing salt doesn't change how quickly something dissolves. But again, back to our other example with Coca-Cola, carbon dioxide can dissolve in bottles of Coke because it's under pressure. High amounts of pressure push the gas into the bottle of Coke, and that allows the gas to dissolve in the bottle. And so when you open the bottle, you've now released that pressure. You've undone all that pressure, and so the gas can now escape. And that's the fizzing of a Coca-Cola bottle or can. How much can you dissolve in water? So the attraction between molecules of solvents and solutes can only do so much. You can only dissolve a certain amount of sugar in water, in a glass of water. You can only dissolve a certain amount of salt in a glass of water, right? After a certain point, you're going to see the salt appear at the bottom. You're going to see the sugar appear at the bottom. So when we reach that point, when it cannot dissolve anymore, you cannot dissolve any more sugar, you cannot dissolve any more salt, you say that the solution has been saturated. You've put too much solute in your solvent. You've put too much sugar in your water. And now the sugar is sitting at the bottom. So you can say that mixture, that homogeneous mixture or heterogeneous mixture, is saturated. It's already full of solute. You can't add more because it won't dissolve. It'll just sink to the bottom. So over time, the attraction between the molecules and what is dissolving is equal. So no dissolving happens. So let's say we had a whole bunch of sugar. We dumped a ton of sugar into water or salt or whatever you want. Well, it's very attracted to the water. It's very attracted to the water. And so the water quickly pulls all that sugar away from this blob of sugar here. And so the blob of sugar will get smaller, like so. But as more sugar is going into the water, the strength of the pull water has gets a little smaller every time. Water can only pull so hard. And so at a certain point, the sugar pulls back. The sugar starts to pull back. And at a certain point, the sugar pulls back just as hard as the water is pulling from it. And when that happens is sugar is being pulled off, and then sugar is being pulled back. And sugar is being pulled off, and sugar is being pulled back. And so you won't see any change because it's not dissolving. It's just cycling. At first, the water is pulling all that sugar off, and the sugar is not pulling back. Over time, as more sugar is being put into the water, is being pulled into the water, the sugar pulls back just a little bit. And when you have too much sugar, the sugar pulls back equal to the amount of sugar being pulled away, and so you don't get any dissolving. And so we say that when these forces become equal, the solution is saturated. So I did say that when you reach saturation, or when a solution becomes saturated, you cannot add any more solute to the solvent or any more sugar to the water. It's kind of half true, because you can supersaturate a solution. So there's a way to get past that saturation point, right? And that is by increasing temperature. You can get past that saturation point. You can increase the pull of the water. You can increase the pull of the solvent. Why? Because when you increase temperature, the molecules move faster. And because they move faster, they can pull that much harder. And so they pull harder. And so they can go past the saturation point. So let's say we had normal room temperature water, and you add a bunch of sugar. And as you add sugar, less and less of it is dissolving. And you start seeing it at the bottom. Okay. If you heat that water up and stir that water, well then, as the water gets warmer, its pull on the sugar, its pull on your solute becomes stronger, and it pulls away more sugar. And so it dissolves more. And so we say when we move past the saturation point, it is super saturated. It is super saturated. And this video will review that. You can find that on D2L. This is a very big lesson. So if you want to take breaks in the middle, feel free to. But this will cover everything regarding mixtures. So now that we know that the solubility of something can change as we increase temperature, we can show this on a graph, right? We can show this on a graph like so. So we know we can change the solubility of something, and as the temperature changes, the solubility changes. So we call this a solubility graph or a solubility chart. So as you increase temperature, the saturation point goes up. So let's take a look at potassium iodide. At 0 degrees, you can only put this much potassium iodide in what you're mixing. Right? At 0 degrees, you only put this much in, 130 grams per centimeter of water. But if you heat up the water to 30 degrees, if you heat up the water to 30 degrees, you can start adding about 180, right? That's the maximum, and as you increase, it goes up. Let's take a look at potassium nitrate. At around 0 degrees, it's about 11 or so. And if you go to 60 degrees, it goes up past 100. Different molecules and different substances, their solubility changes differently based on temperature. So potassium iodide is affected by temperature, but potassium nitrate is affected even more by temperature. You can dissolve more in a liquid as you increase temperature. You don't need to know potassium iodide. You don't need to know the word. You don't need to know these fancy words. All you need to know is you can change the solubility, you can change the saturation point when you increase temperature or decrease temperature, right? So in this chemical, this line represents the saturation point. And the saturation point goes up when you increase the temperature because you can add more solute. So this line shows how much can be dissolved, right? And this line represents temperature. Each line on the curve shows when a solution or a solute will become saturated in water at a certain temperature. So again, at 0 degrees, this chemical is saturated at this point. But at 30 degrees, it jumps up much higher. This is the maximum that has changed. So this used to be the maximum at 0, but at 30 degrees, this is the new maximum you can add. So let's, instead of saying potassium iodide, let's say salt. That was a terrible S, but salt. So you could only add 130 grams in 100 centimeters of water at 0 degrees, for example. But at 30 degrees, the water can take more salt. The saturation point went up. And so it went up to about 180 grams per 100 centiliters probably, of water. So your saturation point can increase as your temperature increases. So these graphs tell us that different solutes are affected by temperatures differently. And again, you don't need to know this much detail. This is just for the sake of being able to read a graph, because on a test I may show you a graph and I may say, well, what's happening here? You should be able to tell me that the saturation point of these chemicals are changing because temperature is increasing or temperature is changing. You should also be able to say, as temperature increases, your saturation point is increasing. So try this. We can try and draw a table with the following information. So you have 0, 20, 40, 60, 80, 100, and try and create a solubility curve that looks like this, right? So from this table, draw this table on your notes, and then try and draw this graph, because you should be able to draw a solubility curve. That's what it's called, a solubility curve of a substance. So here we have, at 0 degrees, you can add 175 grams of sugar. At 20 degrees, you can add 200 grams. At 40 degrees, 235, and so on. Right? So on this graph, you can see that as you increase the temperature of water over time, the amount of sugar you can add in total goes up. At 20 degrees, you can only add a maximum of 200 grams. And then it's saturated. Any more sugar added will appear at the bottom. But if you heat it to 40 degrees, you can add an extra 35 grams. So a total of 235 grams of sugar can be added. And that's basically how you draw a solubility curve. It tells you that sugar can be dissolved in water more as temperature increases. As you increase the temperature, more sugar can be dissolved in water. This was a very long lesson. This will take probably multiple classes, but this video covers everything you should know about mixtures. Again, please know what matter is from the previous lesson. Know that matter can be divided into pure substances and mixtures. Know that mixtures can be homogeneous and heterogeneous. Please draw this out because that'll help you. Know that pure substances are only made up of one kind of atom or molecule, while mixtures can be made up of multiple atoms and molecules. Please know that homogeneous means looks the same. Homogeneous mixtures can also be called solutions. You should be able to give me an example of a homogeneous solution or homogeneous mixture. You should know what a heterogeneous mixture is. You should be able to tell me that heterogeneous mixtures are mixtures where you can detect the different parts. You should be able to tell me what a mechanical, suspension, and colloid are. A mechanical mixture, a suspension, and a colloid are. This is an example of a mechanical mixture, and that's an example you can use on a test. Trail mix, chips, things like that. Mixture of chips. You should be able to tell me what a suspension is. That it's a mixture where the parts settle in different layers. You should be able to tell me what a colloid is. It's a mixture that looks like a solution, but it scatters light. The particles are too small to settle. And you should be able to tell me what dissolving means, which is when a solid or gas is broken down in a liquid. You should be able to tell me what a solvent is, the liquid that dissolves things. You should be able to tell me what a solute is, the solid that is broken down. You should be able to tell me what it means to be soluble. Soluble means it can be dissolved. Insoluble means it cannot be dissolved. You should be able to tell me what affects solubility. What affects how much something can be dissolved. And you should be able to tell me temperature affects how something dissolves because the molecules move faster. You should be able to tell me molecule size affects how things dissolve because big things dissolve slower. And pressure affects how fast gases dissolve. High pressure, faster dissolving. You should be able to tell me what saturated means. Saturated means you can't dissolve anymore. There's no more solute that can be added. And you should be able to explain what saturated is, what being saturated is. You should be able to tell me what supersaturated is. You should be able to tell me how to get a solution to be supersaturated by increasing temperature, because this increases the movement of the molecules. Not super important, but still important. You should be able to read a solubility graph. You should be able to tell me what these lines mean. These lines represent the saturation point, and the graph tells us that the saturation point changes as temperature changes. You should be able to draw a graph, right? This is a solubility graph, but it's no different than drawing any other graph. So you should be able to draw a graph, because I may ask that of you. Thank you for listening, and I will see you in lesson 3.